China's newest radar systems prove reliable on the battlefield, the US's long-held advantages could become obsolete.
Our next story takes a deep dive into emerging technologies like quantum radar, which would make even the stealthiest aircraft lose its most potent capability.
Quantum radar, which could make even the stealthiest aircraft lose its most potent capability.
China just unveiled a groundbreaking 6G powered system that may render stealth jets detectable, even from far distances. This isn't science fiction. Using photonic technology and ultra-fast data transmission, this system can generate thousands of radar illusions while staying fully connected across hundreds of platforms. If verified, this innovation could redefine how advanced aircraft are tracked and identified. In this video, we'll uncover how it works. This one operates on precision. It uses photonic modulation techniques to tailor signals that appear legitimate to receiving sensors. According to published reports, it can connect with over 300 separate systems simultaneously using optical and RF interfaces. This means entire groups of aircraft, ground stations, and surface vehicles can operate as a single electronic web. These are not random disruptions. They are engineered to look like actual moving objects. This is the same range used by advanced systems like the APG-85 radar aboard the F-35 fighter jet. These radars are designed to identify threats while staying immune to traditional signal jamming. But the 6G system doesn't rely on brute force interference. But if all those systems are simultaneously fed false or misleading information, even a pilot inside a high-tech cockpit might not realize the picture is wrong until it's too late. That uncertainty changes how missions are planned and executed. Instead, it generates credible signal replicas, making it difficult for the radar to determine what's real and what isn't, meaning it can act like a legitimate participant on the network while inserting its own manipulated data. It doesn't need to overpower the signal. 6G provides the backbone for integrating AI-driven autonomous systems. If these platforms become mobile, mounted on aircraft, ships, or even low-orbit satellites, they could provide constant surveillance and electronic support over large areas. Stealth jets cost upwards of $100 million each, but if a far less expensive system can consistently undermine their effectiveness with higher throughput, lower latency, and improved security, this could lead to decision-making loops where machines process information faster than humans can react, with minimal delay between detection and action. And that introduces a paradigm shift in aerial systems where stealth is no longer an assurance, but a vulnerability under certain conditions. It may allow for easier integration into civilian systems, broadening the range of data inputs and possibly creating a national-scale sensor web. Every 6G tower, vehicle antenna, or satellite link could become part of a distributed awareness system that functions both in civil and national security contexts. If machines are interpreting digital environments filled with deliberate deception, as digital deception, photonic speed, and synchronized platforms redefine airspace strategy, the question isn't just whether stealth is still effective, it's whether information itself is now the ultimate edge. This breakthrough invites a new era of innovation, adaptation, and rethinking how the skies are navigated, not just superiority. Rather than overpowering adversary systems, the new goal might be to maintain operational integrity in a contested spectrum where signal pollution is the norm. Frequency hopping algorithms and AI-enhanced signal recognition that can sort real targets from synthetic ones faster than human analysts can. How do you ensure trust in the system's response? What safeguards are needed to prevent automated actions based on manipulated inputs? That disrupts the economic logic behind investing in radar-evading platforms. The traditional approach of layering stealth with superior radar and satellite tracking may no longer be enough. New focus areas may include quantum-resistant encryption. Suddenly, the skies are not only monitored, they're digitally mapped, spoofed, and reshaped in real time. Capabilities. It challenges the very foundations of decision-making and system trust in high-tech environments. And it's a preview of what electromagnetic strategy might look like for the next generation of aerospace systems. It just needs to appear authentic enough to pass through undetected. It's a shift toward information-centric operations, where electromagnetic advantage becomes more important than kinetic range or physical durability. With the ability to network over 300 platforms, the system isn't limited to aircraft. It could link up drones, naval vessels, land vehicles, and even satellites, forming a seamless electromagnetic grid. This would allow for shared awareness across sea, land, air, and space, which is critical in environments where real-time information and coordination define success. In simple terms, it's not about having the biggest aircraft anymore. It's about owning the clearest picture and the fastest response. Including X-band, a frequency used by many modern airborne detection systems. And because it's built on 6G infrastructure, it can handle extremely high data loads while minimizing latency. That makes it ideal for real-time applications where every millisecond matters, but scaled up across an entire radio frequency environment. This aligns with the broader global trend towards smart electromagnetic control, where information becomes a key tool in strategic advantage. Why it matters: materials, design geometry, and emission control all work together to reduce visibility to radar systems. But this new development raises an unprecedented challenge. What if stealth no longer guarantees concealment? Blending in rather than disrupting. That's the critical difference. The deception is subtle, continuous, and difficult to detect. It's not about hiding an object. It's about confusing the very tools designed to detect it, creating short but critical delays. And what it means for the future of aerial technology. This platform is centered around microwave photonics. China's new system isn't a radar in the traditional sense. It's an advanced electronic platform designed for high-speed signal processing and real-time spectral control, meaning it can simultaneously receive and transmit signals at the same frequency without interference. This is a major leap from conventional electronic systems that typically switch between sending and receiving, indicating strong institutional support. It's already in early industrial testing or false targets. In this case, both functions occur in real time, enabling an uninterrupted exchange of information even under rapidly changing signal conditions. Built by a team at Huazhong University of Science and Technology, a field that uses light-based components to analyze and manipulate radio frequency (RF) signals at extraordinary speeds, enabling it to operate across different radar bands. The heart of this innovation is its full duplex operation. Specifically, the frequency range of 8 to 12 GHz is particularly noteworthy. This system is backed by 71.8 million yuan, or roughly $10 million, which means it's moved beyond the prototype phase. What sets it apart technically is its ability to create more than 3,600 signal decoys. These decoys can flood radar systems with distractions. This system operates with surgical precision. It inserts deceptive signals into the electromagnetic spectrum, making it difficult for an operator to distinguish real aircraft from electronic mirages. Unlike conventional jamming systems that focus on noise or distortion, equally critical is the platform's network capability. This system also supports multi-frequency adaptability. The development suggests China is moving toward multi-domain electronic platforms, tools that combine data processing. For decades, stealth aircraft have been engineered to avoid detection by minimizing their radar cross-section. The platforms focus on X-band radar, unlike conventional jamming that announces its presence through noisy interference. Modern stealth aircraft depend on sensor fusion, the merging of radar, infrared, electronic support measures, and data links to maintain spatial awareness. More than just visual concealment, stealth involves low probability of intercept, LPI, signals, and passive listening. But this new system works in shared frequency space. The implications are wide-reaching, and cost becomes a factor, too. It's not just about defeating radar. It's about controlling perception. Beyond the technical marvel, the rollout of China's 6G electronic system signals a broader strategic move. One of the most significant features is its cross-domain integration potential. The use of 6G bandwidth also positions China ahead in next-gen communications. Another important consideration is the dual-use potential of this technology. Because 6G infrastructure is being developed commercially for telecommunications, for global aerospace leaders, this means revisiting assumptions about dominance. And it raises important questions about policy and safety. Internationally, this development is likely to accelerate investments in electronic resilience. In essence, China's 6G EW platform doesn't just push forward electronic China's 6G. Enabled system signals a shift where control of the electromagnetic spectrum may become more critical than traditional speed or stealth.